take a function that would take even a function that is already done, like plot, like the pairs we've seen, like describe, and put all of them together. What do we do? That's it. So let's look at the structure of our function. Now, if to do the structure of a function, let's just look at how we can get to see what a function is. Remember, we just use pairs. So pairs, somebody sat down and wrote the function pairs. So all you do is just to call the name. What is behind it, you don't know. All you have to do is to provide it with argument. Now, if you want to know what is inside this function, you write it without the parentheses and then you run. Okay, so let's see. So if we run this, like this. So this is it. So this one, it's like masked. It is within graphics, right? So you are able to get it, but you don't really see what goes in there. Okay, I'll look for other functions that we can. There's a package called reins. So let's install reins. It's like reinsurance. This reins is a reinsurance package, especially for actuarial science. So let's quickly install it. Reins. So install it, and then once you are done, just take it like this so that you have access to it, its content. Right. Now, if you do so, there's a function called ESPQQ. ESPQQ. So that is exponential quanta plot. We will be, first of all, install reins. Once you are done, just do library reins, or alternatively, what do? You load it on the packages session. Now, once you are done with this, there's a function called ESPQQ. Now, if you do the help files for this, it tells you that it's what? Exponential quanta plot. Right? It says it computes what? The empirical quantiles of what? A data vector. We will come back to this when maybe with you do this later on in your maybe second or next week or the following week. Yeah. Okay, so what this function does is that when we have a data set and we want to fit an exponential distribution, let's say the service time of customers at a particular bank, we want to model it. Such times are modeled usually using exponential. Now, I can plot this with standard exponential so that one is on the x-axis, one is on the right and the y-axis. Now, if they face it well, then I expect to get a straight line so that they agree in principle. The more it deviates from the line, the 45 degrees line, the less this distribution is preferred for that particular data. Right. Now, so let's look at this. So if we come here, usage, it says data and plot, right? So let's just take it and plot is through and so forth. So let's just call ESPQQ. Data is equal to, you remember the data we dealt with in the auto BI, right? The auto is what? Auto buy. Good. Okay. So let's go and get the library of, that is in what? The auto buy is in which package? No. It's insurance data. So once you become conversant with, when you are dealing with, maybe later on you are teaching, you realize that wherever the data is, you know the package. But if you don't know that, there's no panic. What can you do to know which package the data set is? The double question mark. Yeah. So don't. Yeah. So let's do that one too. Now then it means that we can check whether the exponential distribution. Remember that the auto BI2, you need data, right? You remember its usage? Yeah, its usage means you have to load it with what? Data. Okay. So now I can call auto BI. And then what was, we want loss, right? Okay. So let's see how this function works. There it is. So it gives us this graph. Parma C4411. That's constant all the time. Here, main, we don't want any title, so we do that. And there we go. Oh, I did not do it. So the question is, does the exponential distribution fit this data well? Well, no. Why is it so? Because you see, it doesn't, it's like a curve. Do you remember the histogram of this data? It's like all of them were in one bar, right? And then, so those outliers is what you see over here. It was around 9,000 or more than, no, I think 11,000 something, right? Million or something. So that's what you see as an outlier. Okay, there's also another called Pareto QQ. So Pareto is also a distribution usually used for modeling income because it's a heavy-tailed data. So let's see how that one fits it. Well, this one too, it fits because it has a longer tail. See, it is able to fit the very unusually large observations, right? But those over here, it doesn't. So if I'm drawing a straight line here, I think it will go through here, and then all these parts will not have any this on it. But compared to the exponential, the Pareto fits the unusually large observations better than the exponential. Is that okay? We can go on and talk about even log normal, which is even more heavier tail than, you see, log normal QQ. So you do all this again with Dr. Sumwa. Okay. So later on, when we give you a data, we'll ask you to be able to fit a distribution. Let's say this is loss data, so it may, let's say you're at an insurance company and you want to model the claims or the losses. Okay, you need to be able to find the model that really fits it. Well, that's why you did probability, so that you know probability distributions. But not only that, there are other distributions. We can't teach you every probability distribution in this one. Yesterday, if you listen to the seminar, you realize that all the MPhil students who presented, they were doing some generation. It's a form of probability distribution. So just like what we are doing now. Okay, so there are distribution that people are still doing research to. In other words, it's not every shape or data has its distribution known now. Okay, so there's an ongoing this. But if you look at all these three, which one will be better for you? So you see, just like we got that scatter plot, we can also get all these on one graph, and then we choose the one that fits. Which one will you use? This is log normal. This is Pareto. This is exponential. Which one is better? Which one? The log normal, because you see that it's able to model both the it's almost on the 45 degrees line. So it's able to model the unusually low observations. It's also able to model unusually large observations. Okay. Now, what brings us here? That these are all what? Functions already built in the package that we got to use. Right. How do we construct our own? Well, let's look at this. So call the exponential QQ like this without the parentheses. And then run it. So what you were doing, this is what somebody did behind the scenes to enable you use it to get all the graph we got. Now, so you look at the structure, it starts with what? A function, right? Then there are some arguments, data, plot, main. Do you get it? Right. Then there is a bracket that is opened. And then within the bracket, you have the body of this function. Okay. And then lastly, there's an output. So the output, you either get what? A plot or something else. Okay. So it is this same structure that we are going to use to construct our own function. So structure of a function. So it needs a name. And then you need this assignment statement. Is that okay? Then you need the keyword function. And then within the parentheses of the function, you have what? Arguments. Arguments. Then, after that, we open curly bracket, we close it. Within the curly bracket, you have the body of the function. So you have the body of the function. Here, the body, or then the body is made up of some statements. It may be computations, what have you. And then usually we will return something. Okay, so the output, we will use the keyword return, and we will return what? Maybe results. So this is the structure of our function. It has a name. We have the less than with the minus sign, the function arguments it will take, the computations we will do, then the results we want to see, and then the brackets are closed. Is everybody okay with it? Please, are you okay? All right, okay. So now we want to spend so much time on it. We're just going to do something small to help us understand this, and then it's up to you to use it anytime you want to write your own function. Okay, so now you know of the BMI, right? Usually when you go to hospital, they can put a machine over there, you step on it, it calculates your height, your weight, and then it gives you the body mass index, right? We can write a simple R program to do this. Right. Okay. So now what I want you to do is that we want to write a function to compute BMI. Okay. Now, if we go to Google and we type BMI, you can get, let's say, BMI calculator. Okay, so it says, so this is the classification. When your age, it doesn't really take age anyway, but it's just your height in meters, weight in what? Kilograms. And the computation is that it is what? It's weight over what? Height squared. That's why each unit is what? Kilograms over what? Meters squared. Is that okay? So what this function is that we need to feed it with what? The height and weight of the person. Is that okay? Then that small computation will be done where it divides the weight in kilograms by what? The height in meters squared. And that gives us what? The BMI. Is everybody okay with this? Okay. So if we are going to write our function will take height and weight as arguments, compute the BMI, then we are going to report the BMI and what? And the height. Now you can even go ahead and do the classification such that it will tell you whether this is the person is obese, normal weight, and so forth, just like you have over here. Right. Okay, so let's go back. So what is the name of our function? Let's call it BMI fun. Is that okay? Then we need the assignment statement. We need the function. We said it should take in what? Height and what? Weight. Oh, weight should be HT, right? Like this. Right. Then we have to open the bracket and close it. Then we work within the bracket. Okay. So here we'll call our BMI to be what? Weight divided by what? Height squared. So height squared, there are several ways we can do this. We can do so by raising it to the power 2. Alternatively, we can do what? Height times what? Height. Or it can also be what? Height. I think height. There's another way to do this. Height. Yeah, there's one more way. Fine. Yeah, I mean, we have one. There's one more way, but I can't recollect. Okay, so it's fine. We can do away with this. Right. Okay. Then remember that the result is now BMI, right? But I don't want to just get a BMI. It would be good if I record the height, the weight, and the corresponding BMI. Is everybody okay with this? Okay, so it means that then that's why we did data structures. So now I have my data BMI, but I want to combine it with what? The height and weight and get it out. So what do I have to do? I may call it tab, then I use C, right? So I record the height, I record the weight, I record what? BMI. Okay. Now, if you want, you can name it. Do you remember we did all this in the vectors? Yeah, we can name the tab, and the naming will just be like this. So I copy this, I see the way I'm typing, so I'll finish right now. So I just copy the same thing and then I put them in what? Quotation marks. So now that's my result, so I can return what? Tab. Well, I may want to also, I don't want to complicate things, but let me do a lazy way of doing this. So I can round it to, let's say, 2 decimal places. Otherwise, we'll get too much, like 5 decimal places, right? So this is it. So we've written a simple function which takes height and weight and then output what? The BMI together with the height and weight. So now let's do this. So when you finish, you have to run it. Once you run it, come to your environment. You see that you've created a new object. If you remember the package, we said that a package is what? It contains data set, functions, or both. So you see that your environment now has data set, and it has your user-defined function and listed under what? The function. So let's write this quickly, and then so when you finish, you have to run the function. If you want to run it, you can put the cursor here at the far end, or you highlight all of them, but I don't advise that because sometimes you highlight and part of it will not be highlighted. You run it and then there's a mistake. Okay, so usually it's important that you do what? You just put the cursor at the end of the curly bracket, run it, and then once there's no red, then it means it runs successfully. Then you go to your environment to check whether you have it over there. Once you have it, then that's it. The next thing is for us to now input in height and weight, and then check whether we will get our result. If we pull this one, how will it will then represent it? If the let's see. Is it better this way? No? It's not. If I clean this way, but it will still not be better. Is it better? You? Are you done? If you are done, run it. Once it runs and you see it, yes, so yours is successful. You have to go to your environment, check whether you see the function there. That's all your environment. That's history. Okay. So you must see functions and the name of your function there. Then I'll call it, you call the name. So it will be BMI function into parentheses. Then you look, give it height and weight. Maybe height is equal to 1.7 meters. Weight is maybe the answer 160. Then we'll go online and check the BMI, whether the person is obese and so forth. Is that okay? So let's do that quickly. are you done? Yes. Yes. You have to use the function. We are not writing it for right. We want to use it to calculate BMI. Okay. So what we need to do now. What we need to do now is to call the name of the function. The name is what? BMI underscore function. So we call it just like the way we were using pairs, plot, summary, describe, it's the same thing. But now the BMI function is for us. We wrote it. So this. Then it needs height and weight. So the height, let's say the person is 1.75 meters, and we said we want the answer, so 180 kilograms. Okay. Now let's run it and see. So this is it. 1.75, weight 80, 180. The BMI is 78.78. 58.78. Did you get the same? Okay. Now let's go online and check. Let's check any BMI calculator online. And let's put in 1.175, right? Centimeters is the same as 1.75 meters. Then this one we have what? 180. We said the answer. So then you click on it. Okay. So it says the BMI is what? It's exactly what we got. And what is the classification? Okay. Now we can also go back and change the weight to, let's say, somebody who is suffering from, let's say, anorexia. So let's say 60. Is 60, maybe 50. What will happen? 16.33. Right? Let's go there and change the weight to, was it 50? 50. Calculate. This one is moderate thinness. Are you having problems? So we can actually go on and also classify this. That will lead us to what we call conditional statement. If you are this, that, else this, else, and else. What's the issue? I think you did not. Nothing shows. Okay, so it is telling you that weight not found. You see, I use capital. If you use, you have to check. There is a weight and weight, small letter weight and capital letter weight. They are not the same. Okay. Is it working now? In BMI, so unused argument weight. So the weight you have at first is small, and you have to be consistent. But you have to rerun it. No, that is small letter. Let it be cap. Are you sure it's cap? Do it. Write another one, the opposite beside it. Then you will know whether it's cap or not. Okay, now it's working. So, R is case sensitive. Please, any question? Okay, so what I want us to do is that we are going to use this to learn about what we call conditional statement. If we have a condition, so for example, if it rains, I will not come to class. Okay? if the population is greater than, or maybe the population size is greater than this, then do the classify. You can use it to classify stuff. So conditional statement. We'll just do if and if else. There are so many of them. This is not really programming class.
Say,
yes.
I was wondering, like, the height, why should we like height equal to 1.75? Because the function, we know that the height is, are we supposed to write height equal again?
No. Okay, so they.
Would you work without writing height equal?
Yes, but it's a dangerous way of programming. So, because calculations, this may be, it may be money or decision to give somebody an education or not, and so forth. So, can you imagine if I swap it and height becomes your weight? Do you get it? So, it is important that when you are giving values to argument, you keep the argument there, so that whoever sees it will know that this is equal to this. I can run this, as I said, by just giving BMI, let's say 90, maybe 1.65 and then 60. So it will work. I'll get my BMI. It will tell me that height is 1.65 because I can assign true positions. But that is dangerous, as I say, because you can easily switch them around without knowing. Yeah, so that's it. Okay. All right. Now, so conditional statement. Conditional statement. Okay, so 1, we have if else. No, if else. Now, let's look at what if else is. So, what does it say? It says conditional element selection. What this means is that if else, so we have a condition. If the condition is satisfied, you do this. If it is not satisfied, you do the other one. So, this is a condition in which you have two outcomes. If the condition is satisfied, you do this. If it is not satisfied, you do this. That's it. You can't move on. Okay. Now, so let's see. For example, tomorrow they are going to vote, right? So, I can write a conditional statement that if the transport that is giving me is above 100, I will go and vote. It means if you come and you give me 50 cedis, I'll take the money, but I will not step at the police station. Is that okay? Okay. So now, let's look at it. We will say cash. And for cash, we take 20. So maybe this person gave me 20. The next person gave me 700. Next person gave me 50. Next person gave me 80. And so forth. Now, what we are saying is that if the amount given is greater than 100, I will vote. Else, I will not vote. So that's how this if else is. So there it is like this. If you do the help files, it tells you if test, yes. So if the test is true, the yes is computed. Other than that, what? A no is computed. Okay. So let's see this. If else cash is at least 100, vote, or let's say I'll vote. So the yes means I'll vote. The no means what? I will not vote. Now, why didn't I write this? I will not vote on its own, but I put it in quotation mark. Why did I put this in quotation marks? Because it's a string. I cannot write a sentence, I will not vote it now, and then it won't. Okay. So now let's see. What will happen? Okay, object. Why am I getting this? Small letter, capital letter. Good. I've not run cash. So if you go to environment, there will be no cash there. Is that okay? As soon as I run cash, then this one, you see the first one is 20, so I will not vote. The next one is what? 700. That is beyond my expectation, so I'll run and go and vote. The next one is 50. Below expectation, no vote. The next one is 80, no vote as well. Is everybody okay with this? You can use this, for example, in tax. Okay, so if let's say you earn less than this, we give you this tax and other than that, this tax and but that is on condition that there are only two options. If it is more than 3, you cannot use this. If more than 2, you can't use this if else. Please, is everybody okay with this? Okay. So now let's look at the one that will be general. 2. If else. So we've done if else together, but we are now going to separate if else. Right. Now this one, essentially what happens is this. You have if, what if condition, if the condition is satisfied, do this. Else, if it is not satisfied, do it. So for example, grading, right? In your grading, we know that 80 to 100 is what? A. 70 to 79 it's not 75. I think it's this. B plus. No. 60 to 69. B. 50 to 59 is what? C. This one we don't want you to get it. Because once you pile it, then you are below 2.5 and we can't graduate you. So if you get C, we can't graduate you. Then there's D. I think D should be 40 to 49 or something. This one is failed. And then below 30 will be what? F. So I think this is a grading scale. Okay, so what we are going to do is that we are going to write, this one has several options, so we cannot use if else, right? So what we are going to do is that we start. If the score is greater than or equal to 80, we assign grade to be A. Else, if it is greater than 70, we assign B plus. I don't need to give the endpoint because if it is 90, I won't even get to the second one. Do you get it? Yeah, so you can probably, but it's redundant. Anyway, so that's the sort of thing we do here. Okay, so let's look at it. So here we are going to say that if score is greater than or equal to 80, we are going to say that grade is assigned what? A. Is everybody okay? Then after this, we say else if, because I haven't finished, the last one will just be else. So else if score. So I can copy this and paste. The grade will be what? B plus. So this one I'll change it to what? 70. Please do. So this one, it means the score should be greater than 80 and what? Less than or equal to what? 100. But I don't need that part. You can, if you do so, then it will limit it. So it means if you put 50 in there, you will not get any grade. So we move on. So we can just copy and paste like that, and then we change it. So this one will be B, and this should be what? 60, right? And then I do it again, and that will be 50. That should be what? Oh, is it 52? It's C, right? Good. And then last, then we have D. That will be 40. Please, are you following? That will be D. Let me put this here. And then lastly, else. So the last one, I don't need else if again, because the rest is anyhow. Grade is assigned what? F. Like this. Okay. Now this, it will be, for me to be able to run this, it means I should have a value for the score. Do you get it? Yeah, I need a value for the score. So for example, let me say score is 30. What do you think the value will be? The value of grade. If score is 30, the grade will be what? So let's run this and see. Oh, there's something unexpected. I get it. That's one thing with this. The last bit needs to come like this, otherwise, no, something is wrong. I did not put else if here, that's why. So you see, when you are copying and pasting, you have to be careful not to. So I left out the else if from here. So I can put else if, and then lastly else. So let me see. Did it work? Unexpected else in else. Something is wrong somewhere. So I start, if score is greater than 80, grade is A. Else, if the score is greater than 70, grade is B. Okay, yeah. I need, the else needs to follow exactly after this. Other than that, it won't work. Else if, then else if. Okay, let me try again. There we go. So now we all know what grade will be. So let me call grade. Grade is F. You remember the score was 30. 30 is F. So I can change, I can go back and change again. So please let's see. But to make this work, I can put this in a function and call the function grade. So I put the value in and then it gives me the grade. I can also bring the value and the grade, just like we did earlier. Okay, so maybe we can do that. So put this in a function. So in a function, that's going to, we are going to call it grade fun. It doesn't mean that every function must come with a function, right? So this will take score, and then once it takes score, you put this one in, and I can do my tab as that will be difficult because what will make it easier? I think cut, because if it is a vector, I cannot be inputting a vector and a vector that is made up of the grade, which is character, and the mark, which is what? A value. Okay, so what I can do is to use what we call cut, which means you write or paste rather. Yeah, I think paste. And then I will say the grade for I can actually put the number, the grade for, then I'll put score, and then I put this is grade, right? Do you know what I want to write? So at the end of the day, my function will paste this on the board. The grade for score, there to be the value, is this. So let's see how this works. So it is called grade fun. Let me put in 90. So we can do this as well. Okay, so you can play around with R, and it can be very interactive, depending on how you want to look at it. So what I have done is to put all this. I don't know. Maybe I have to collapse this. Is to put all this in what? In a function. I just copy. Don't write again. What we did over here, if it works, then I put it in a function so that I don't, it makes it easier for me to use. So the function is called grade fun. So it takes the function to go through all and select the grade and show you the grade. But instead of just writing the grade, I now tell the reader or the user of the function that paste. So on my console, it gives you what the grade is. Yes. So the top will just be the function. So essentially what we did up there, copy it and put it in a function, but that function must receive score as what? Its argument. So the conditional stuff is what we call argument, and we can have iteration as well, like for loop and all those stuff. I don't want to turn the class into purely programming course. What we want to do is to be able to do statistics. But these are very important. You need them as well in making decisions. Are we okay now? Please, are you okay? You are having problems. As I said, please look at the way if you are having problems with the else if, see the way I arrange this, because they can make life uncomfortable. Are you getting nervous? Is your listen not too small? The font. Just increase it. So control it plus. Yeah. It's then minus. Okay. So the paste, they can take string and stored values and so forth. If so, the conditioner has length, yeah, you cannot, you can't do this. If you want to do that, we have to take them one after the other. You can't pass a vector to the egg. Yeah, so if it is the function, I can also get the scores and use, let's say, S apply on the score, then I put a function on it. So it will take each one and do. So you write the function first. So it will yeah. Of the score not found. Yeah. Wait, because you don't have, your function does not end. You haven't done any function because the function must, if you remember, the function must have a name. Then you open the curly bracket. You have not opened the curly bracket. Everything within the function must be inside the curly bracket. So highlight all of them. After the function, highlight it all up to the last, and then put them in the curly bracket. No, run it first. Let's see what other function is first. No, run. public facing issues. Okay, so now that's it. Now, so we've done a bit of programming. Let's get back to our data analysis. Thought we are closing. The way you are laughing. That one is a closure laughing. Okay. So we've done a bit of programming. This helps because sometimes you want to now. So what I want us to do now, let's look at our. So we've done some control flow, this exploratory data analysis. We've done some probability distributions, a bit from what we have done. Hypothesis test, 1 sample, 2. You have done hypothesis, right? Good, okay. So let's start with this. You've not done hypothesis testing. You shake your head and then you are hiding. Okay. Now, let's look at this. But I'll send you some notes on it. Let's see. Okay. So, I think I even have a video on this with some notes on Bivariate, right? Okay, so when we have, remember that last week I think we looked at the car's data, right? Yes. The braking distance of a car. Okay. Now, let's look at, so Bivariate data, in this case when we have categorical, then we will come back to the, what do we call it, the quantitative one, right? So categorical or what? Qualitative. Okay. Now, in some cases, you want to, with a composite bar graph, do you remember? By, let's say, contrasting whether, let's look at this data, the survey data. So if you look at the survey data, oh no, I think it's in mass. So click on mass. So student survey data is some data frame that contain responses of 237 statistics 1 students at the University of Adelaide to a number of questions. Now, sex, writing hand, span of the writing hand of the student, left, right, fold your arms, right on. So when we say fold your arm, is the right hand on this, or like that, or neither will be like that, or something like that. Okay. Now we can check whether, let's say, your sex, or let's say your smoking habit has any influence on your exercise. How often you exercise? Is that okay? In this case, all the 2 variables are all qualitative. Is that okay? Please, is everybody okay with this? Good, okay. Now remember that when we were looking at this, we constructed a contingency table. Do you remember? How do you construct a contingency table? The table, yeah. So we'll call table, in this case, survey. Then we take your smoking habit, and then survey, we check your what? Exercise level. Now, what test can we use to check whether there is a relationship between smoking habit and your exercise, the level of exercise? We can use what test? Yes, what hypothesis test can we want to check whether there is actually a dependence. In other words, if I know your exercise habit, can I determine your smoking habit? Regression? No. Time series? Wait. Yes. Chi-square, do you remember? Chi-square, which of them? There are 2. There's goodness of faith. There's also test of what? Independence. Which one should we use? The independence, yeah. That checks whether there is a dependency in this. Okay. So when you have 2 categorical variables and you want to check whether there is some degree of association between them, what you use is what? Chi-square test. Now in R, we can use what we call chi. So there it is. Chi, so it says Pearson's chi-square test for count data. You remember this one? We counted how many smoke heavily and they exercise often. How many smoke heavily and they do not exercise and so forth. So that's a chi-square test. So let's do like question mark of it. So a chi-square, you can give x and y, or you can also pass in a table. Okay, so S can be what? A matrix. Okay, so let's look at this. So if we want to use it, we are going to just call chi-square. And then we put in our contingency, right? There we go. But there's a warning, and we are going to look at all this. So I'll give you some slides. You see this. Okay. So it says that Pearson's chi-square test. Do you remember in your test you calculate the expected? You have the observed, expected. Then you subtract the observed from, the other way around. So observed from expected, all squared divided by this. Then you sum up. It's the same thing we are doing here. So the chi-square value is what? 5.44. The p-value is quite large. Remember here, we are testing. We reject H naught. H naught is that there is what? What will be H naught? They are independent, which means there is no relationship. Okay, so if we reject, it means they are what? They are, there is association. Okay, all right. So that's it. So in this case, the p-value is quite large. So what do? We fail to reject the null hypothesis. What does that mean? What do you mean by independence? People will not understand. Is it relationship? Yes. These are categorical variables, so interpret it well. Yes. So it means that if I have your exercise level, it doesn't really help me to categorize you, categorize you into your smoking habit. Is that okay? That's the sort of idea we are getting from here. Okay. Now, but there is a warning. So it says that chi-square approximation may be what? Incorrect. Now, why is it so? Who can tell us? Look at the table that we have. Yes. So the key thing is that you must have enough count within a cell. So if we don't have enough count within a cell, the approximation may not be right. So we have to use a test that is suitable for what? Smaller cell count. And such a test, so this is chi-square test of independence. Independence. And then, so when we have small samples, so now we are doing your estimation stuff that you were doing. This is where you put it into what? Into practice. So when you have small samples, we resort to the Fisher exact test. Those of you who listened to yesterday's talk, Fisher came in there. Fisher exact test. Okay. Now in R, so I'll give you this. You see, the Fisher exact test is Fisher dot test. So this is exact test for what? Small samples. So you realize that in the sample we have some less than 5. So you can use the Fisher exact test. You can also use the G test, which is a likelihood test as well, to do so, right? And so forth. Okay. So Fisher exact test. So if you look for it, Fisher. So there it is. So it says perform Fisher's exact test for testing the null of what? Independent of rows and columns. Remember, the rows are what? Smoking habit. Maybe the columns are what? The exercise habit. Right. So Fisher exact test, we also give it the contingency. And there we go. So it says Fisher exact test for count data. P-value is 0.41. So what do? The p-value is 0.41. Are you sure we reject it now? Let's say if our alpha is equal to 5%, then it means that we only reject if p-value is less than what? 5%. Is that okay? In this case, what is your p-value? 41%. You fail to reject. Yeah. And when you fail to reject, what does it mean? It does not have effect. So that's it. And of course, you can use the G test as well, the likelihood test. As I said, I'll give you this so you will see what these are. So is everybody okay with this? When you have two categorical variables, you can do this to check whether there is some sort of independence between them. You can talk about the Kramer's V, a whole lot. There are so many of them. So chi-square, the theory, the function that we use in that. There's also this scenario. So let's look at this scenario. So this is the case where you have, we are going to teach you this. So this is how you write your thesis. So this is LaTeX, and we'll teach you later on after your exam. Okay, so let's see. So look at this one. So a hospital in Accra wants to verify if blood type distribution in the appearance sample matches the expected distribution for West Africa. Okay, so in West Africa, the type O, so maybe from World Health Organization database, half of West Africans have what? O, let's say positive, negative. 25% have A, blood type A, 20 are of blood type B, and AB is 5%. So AB, they are not many. Okay. Now, if a hospital in the okay, so the hospital, okay, so yeah, I'm looking for this. So the sample size is 200. So you collect 200 blood samples, okay, and then you want to check whether it conforms to what West Africans are. Okay, now this is what we call goodness of fit test. In your inference class, you realize that you calculate expected, what is expected, and what has been observed. Okay, and the same thing, you subtract the expected from the observed, okay, and so forth, and then you get that. We can do so in R as well. Okay, so that test is also a chi-square, but here remember that we have the observed, which is out of the 200, 110 are O positive, 50 are A, 30 are this, and AB is 10. But remember, in the West African one, 50% should be what? Should be O positive. So these are the expected, what we should expect in West Africa. But this is, for the 200 that we got, 110 were O. This were that, this were that, this were that. So do they conform? That's goodness of it. And this is a test that you can also encounter. Okay, so we can do this. It's like from first principles. Okay, you get the expected frequency by multiplying 200 by the percentages. How do you get these percentages? Well, you go here. 50% is 0.5. This is 0.25. This is 0.2. This is 0.05, and so forth. So that's what you see over here, like this. Then the expected, we multiply this by the expected proportions. If you print it, you get the results. And then your chi-square test is now what? The observed. What is observed? This one. The values. Then the P is the expected proportions, which are this. Okay. And when we do the results, you get it. So the expected is this. The chi-square value is 2.5. Here you are interested in the P value. The P value is 0.475. What do? You fail to reject. What does that mean? This one is no effect. So you are checking whether the blood distribution in your sample conforms to what is expected in West Africa. Okay. So what will be the interpretation? If you fail to reject the null hypothesis. Remember, the null hypothesis is status quo. It's like there's no difference. Is that okay? No relationship, no association. They are independent and so forth. So what should we do? Hey, my dear friends.
So the black does not conform to that of the West.
It does not conform. Okay, so it's actually consistent with the expected West African blood type. And of course, you can do manual computations like this, okay? And this is what you would have done in your inference class, okay? So like that. So it's just like from now on, you are just going to implement what you've been learning in the statistical inference, okay? So test of independence, we are not so much into it. Mobile phone preference. Let's see. A telecommunication study examines if mobile network preference depends on geographic region in Ghana. In your project, you may be doing some of these things. And when you collect your data, we expect you to be able to use how to get your output, interpret it, and make recommendations and so forth. Okay. So we can create a vector of regions: Greater Accra, Ashanti region, Northern region, and then the columns MTN, Vodafone, Airtel, Tigo. So this is our data. You remember row names called, so you can get your data. So you view it, it's like this. So this is our table. So you see this is a contingency table, isn't it? Which talks about observed network preferences by region. So if you take Greater Accra, MTN leads Ashanti, ask for them every time like that, by the service. And the others, Yamutu. Okay. So how do we use how to do? You should be able to do some of these things, right? Like that output, and how do you interpret it? So that's the sort of thing we want you to be able to do. How do you visualize this? Remember the bar graphs, right? That we did. We can use that to do so, and so forth. So let's do Fisher's exact test. I've talked about it. That's when you have very low observations, right? Then you use Fisher observe test to do it. So for example, you see this one, 2, 4. If you use chi-square, the approximation may not be right. In other words, you may reject when you should not. So you can commit what? A type 1 or a type 2 error. If the observes are very small. So in that case, you use the Fisher exact test to do so. And sometimes it can be used in clinical problems. Okay, so treatment recommendation, conduct larger trial to confirm findings and so forth. The G test is also likelihood test. You may not have done all this, but once you know one, as for the software, once you know how to do it, it's just a matter of searching for it and knowing that there's a p-value. You know how to interpret p-value. So any test you take, even if you don't understand the test, you are now looking at the p-value, because that's for that you can use it to make your conclusion. So here, even though if you have not done it, there's no problem. So you need a package DEX tools, and then there is all G text X and P. So the X will certainly be what? Your data, then the P will be the proportions, and you can do so. Observed, expected differences, and so forth. So this is how you do this. I'm not meeting you again, but I'll tell Dr. Somwa will now start from when you have two quantitative variables. Remember we did correlation, right? You looked at that, so we do correlation, you test it to see whether, like the way we are doing, whether they are related and so forth. And then we go to t-test and so forth and so forth. We'll meet again in the after 608. We'll do test hypothesis test into details and also how to fit distributions and so forth. All right. Okay. So I'll give you your next assignment, and then on this, and then next week you print all the 4. You keep it together. You can just clip it. Don't waste your time with combining. And then you give it to me. So I'll mark all, and then we'll use it as your Yes.
You mentioned that we can have the exams as a project, then we present.
Yes. So in that case, you have to, but that's even on your. You do like this, they will be there sitting and asking you a question. We will see. Yeah, more than one. Not me alone. That's what we can invite people to come and sit. Then you teach us. Yeah. Okay, so have a good night. I'll send you the script.